Welcome to Physics Studio. So far, having discovered that when a charged particle goes into motion, it creates a magnetic field around itself, and that magnetized charged particle will be acted on by a magnetic field from another source, we can see theoretically that we have a path to converting electrical energy into mechanical energy or work. And what we want to look at today is the very surprisingly simple and ingenious set of principles underlying the way we've come to do that. So what we're going to study is the motor. And you know that a motor is a device for converting electrical energy into mechanical energy or work. Now, you're asked you should be on page 2 of your notes right now, but you're asked at the beginning of that to think of 3 appliances at home that turn electrical energy into kinetic energy. And so let's take a look at a few of these. And we'll see what they have in common. So let's see. Number 1, we have a power saw. A power drill. Oh, hello. We have a sewing machine. And you can see what my partner's doing here is making masks for the local hospital.
Let us know if you need one.
Let's see what else we have. Blender. That was not one of the examples. Let's see if we can find one more. Watch out, it's going to be messy down here. Okay, and again, we're looking at appliances that turn electrical energy into kinetic energy. This is a dryer. Now, we can ask ourselves, what do all those examples have in common in terms of the type of kinetic energy they're producing? And I'm going to take a wild guess that you figured this out, but they all rotate, right? None of these machines produces a linear motion that goes back and forth like that unless they use a cam. So let's take a look at why that is, why these machines all use circular motion. And to begin, we're going to take a look at, by analogy, a simple old school playground toy. These are not allowed anymore because too many kids got hurt. But anyway, this is called a merry-go-round. And basically consists of a rotating disc. And then you have some guy, usually the older sibling or the father out there making the thing go around. But I want you to watch what he does to make it go around. Right, he reaches, grabs. Well, he's slowing it down now. Okay, now watch when he gets it going again. Pulls. So he's successively grabbing the bars that are situated on the edge of that. And I can't set one of those things up here, but I want you to imagine that I've got one of these merry-go-round devices right here. Right now I want to get it going. I'm going to plant my feet on the ground outside of the rotating disc. And I'm going to reach and I'm going to grab an iron bar and I'm going to pull on the bar. And when the bar gets right here, I'm going to push. Right, then I'm going to reach again. I'm going to pull to here, then I'm going to push like that. And think about what would happen if I pulled to here and then continued pulling, right? I'd start oscillating it back and forth like that. So the key here is pulling right to where it's in front of you and then pushing. And if you do that repeatedly, you can get that thing spinning quite fast. Now, what does that have to do with electric motors? Well, there's a property of magnets that they can either repel or attract. And attraction is like a pulling force. Repulsion is like a pushing force, right? So if we could get a set of magnets to where it's attracting, if we put one set of magnets on a rotating disc and then attracted it with the pole of one magnet and then flipped the magnet, we could then push it. So on your notes, you're going to see a diagram like this. And you want to look down here at these two, 1, 2. Take a look and see what's different about those two. Right? What's the principal difference? And if you observe carefully, what you notice is that in this top one, the south pole of this magnet is toward the rotating disc. And in this bottom one, now the north pole is closer. And what's happened, of course, is the person with their hand, they simply mechanically flipped it like that. But here, if this is rotating in a counterclockwise direction, this south pole of this magnet, being held outside the disc, is attracting this north pole. Right? And as soon as that north pole gets right there across from the south pole, you flip it, inertia carries it past, and then this north pole repels that. And that's the pulling, right? Pulling and then pushing. It's exactly analogous to that playground toy. Now, by the way, think about a Tesla, right? The car, what kind of motion does that produce from electricity, right? The circular motion of the wheels. All right, now, there are tools that rotate upwards of 18,000 RPMs or revolutions per minute, like dentist drills and other industrial machinery. So that process of switching the polarity of the magnet that's outside so that you're pulling the rotor at one point and then repelling it at the other, that process of switching mechanically is too cumbersome. If only there were a device that could instantaneously swap the polarity of a magnet over and over and over again, then we could solve the problem. Oh yeah, an electromagnet. We know that if we have an electromagnet, we make this the positive pole, this the negative pole, we apply the current circling like that, so we're going to apply our right-hand rule and find that that's the north pole. That's the south pole. Right, and so say we have this rotor that has magnets on it. Let's say it's rotating clockwise like that. And we have a north pole magnet here. And a south pole magnet here. And so on, if we keep reversing like that, so that we have north here, south here, right? As this is turning, this south pole of this electromagnet is going to attract that. And then it's going to be pushing that south pole away. And so this thing is going to rotate up here, right? When that north pole reaches right here, right in front of that, we're going to swap the polarity. And when we apply our right-hand rule, now the current's circling this way, we curl, we find the north pole is this way. And we do that right when this north-facing magnet is right in front of it. It will then start to repel and push the north pole and attract the succeeding south pole coming up, like that. And if we can do that with sufficient precision, we can get that thing rotating at almost any speed that we want. And so the minimal parts of a working motor are, first, you need what's called a rotor. And that's going to be some part that's free to rotate. And on that are going to be fixed permanent magnets in alternating polarities like that. Now, it's also possible to put the electromagnets on here. But then you'll also need a fixed housing to which is attached an electromagnet that can switch polarity. And the fixed housing is like the ground the guy stands on when you can't apply that force if you don't have a fixed position to do it from. So we fix this to the housing. And then we have an electromagnet. I'm not going to put that there. And then finally we have a device here, which is key, which is called a commutator. And the job of a commutator is to swap polarity. Exactly when the rotor magnet passes. And if we have 12 magnets on here and it's rotating at 10 revolutions per second, that means it's going to have to do that 120 times a second. But we can do that. We can get that kind of precision in. So, the basic features of a motor, the basic minimum necessity, you need a rotating element, you need permanent magnets with alternating polarities, and you need an electromagnet that can swap the polarities. Now, we could do that by taking a battery and going like that back and forth, right? But, you know, we have alternating current to do that. So, that's basically it on motors. And I feel kind of bad because we have a really good lab on that, but it requires some specialized equipment, and I don't think we're going to be able to do it. So, we'll try to get some simulations or something for Monday and Tuesday. So I hope that helps in understanding how this works and why all our appliances spin when they do that. Now, Monday and Tuesday, we'll also look at a generator, which actually is kind of more simple than this even. So have a great day or weekend, and I will see you again soon.